Okay, hello everyone. First of all, thanks to the organizer for such a nice workshop and also for providing the opportunity to present here. So today I'm going to talk about Tensor Network, or our recent advancements on Tensor networks, and basically its application for material simulation, quantum chemistry, and also its application in quantum simulation. By quantum simulation here, it means simulation of quantum circuits. And also talk a little bit about the challenges that we are facing to also improve this algorithm by itself. So first of all, I will give you a little bit of overview on the Tensor network. For those of you who are not familiar, a little bit of introduction, and then tell about what are the challenges that we are facing to simulate different systems, including, let's say, structure of materials, as well as different topologies which may be relevant for connectivity between qubits on different quantum computers. And then in the end, give you some application and examples for basically material simulation as well as circuit simulation that we did in collaboration with our colleagues at Multiverse. Okay, so first of all, probably you might have heard the name of Tensor Network as quantum-inspired approaches in the community, but basically when we say quantum-inspired, we usually refer to Tensor Network methods. These are the basically approaches that could, so to say, in a general sense, refer to a higher dimensional linear algebra that can be applied to many different fields, and they have application originally, they originate from quantum physics, but immediately found application in other fields such as high energy physics, quantum computing, machine learning, and many different areas. But before I go into the details, let me give you a little bit of overview of what are tensor networks, and basically introduce the languages that we are using to work with these. So first of all, tensors, what are tensors? Tensors are multidimensional arrays of complex numbers. Probably anybody who has worked with a computer, you know how to create arrays in computer. But to work with them, we introduce these graphical notations, which helps us better to work with these pictorial representation of tensors and how they can be used for representing, let's say, quantum state. So basically, you can represent any tensor with a circle, and then any dimension for that tensor can be introduced by a link. For example, a vector is a tensor with one-dimensional with one dimension. So that's why one link is connected to it, and basically this link connects to the dimension of this vector. A matrix is a two-dimensional basically array, and it has two links connected to it, and then you can extend it to n-dimensional tensor. A scalar is basically a tensor with no link, which means it's a zero-dimensional tensor. So not only this graphical representation helps to work with tensors, but also it can be used for showing some algebraic operation between tensors, such as like summing over shared indices. Like here we have two matrices that are multiplied together, and then there is a sum over this beta index, which is the shared index here. So this operation can also be shown graphically with this notation. So this operation, or sums over shared indices in generic sense, are called tensor contraction. So in future slide you will hear about this too much. So but why tensor networks are good in a generic sense, like in every field, not only physics, is because they are providing approaches for providing compact representation for basically data or quantum states. So as an example, consider this big object, so which is a basically n-dimensional tensor, and each dimension basically has size d. So you can see that the number of parameters in tensor scales d to the power n, which grows exponentially, which is very inefficient. However, tensor networks provide approaches that allows you to break these big objects and represent it as the product of smaller tensors. So still these dimensions are d, similar to here, but a new degree of freedom arises here that later you will see it refers to quantum entanglement, and you can represent its size with chi. If you are lucky and you can basically find a small size chi that basically this network of tensors can provide a good approximation for the original tensor, then it means that the number of parameters in this one basically scales polynomially with the number of tensors, their dimension, and this chi. So basically, tensor networks provide a very efficient representation for data, and how we can use it in quantum physics. So in quantum physics is basically, I think you have seen in previous two talks that there are challenges for finding the ground states of quantum many-body Hamiltonians. For example, Let's assume that you have a system of a spin 1/2 particle. Each one of them has two states up and down. The Hilbert space basically grows exponentially with the number of spin, basically 2 to the power n, which is very efficient. So if you define a Hamiltonian in this subspace, such as H, it could be any generic Hamiltonian, and find basically its ground state in the generic sense, this many-body wave function, which could be the ground state of this Hamiltonian, is represented by this. And this psi I1 up to In is basically the many-body expansion coefficient, which is very inefficient, and it grows exponentially with the system size. However, tensor network techniques allows you to break this many-body wave function, or let's say this many-body expansion coefficient, in a very efficient way and represent it in terms of smaller tensors. So in 1D, typically this representation is called matrix product state. Basically, you have the same physical dimension as for example, for spins, and you have a new degree of freedom. So in previous slide, I showed it with chi. Sometimes people also showed it with D. But this D is basically the amount of entanglement that you can find between, let's say, bipartitions of the system on every links of the lattice. So this is MPS in 1D, but you can also extend this idea to higher dimensional system. For example, in 2D and 3D, we call it PEPS, or projected entangled pair state, and also there are some scale invariant versions such as 3-tensor networks or MERA, which basically I'm going to mainly focus on this one. So in a very short sense, tensor networks are basically, tensors are like pieces of Lego that you can put together to build an object such as house. So you can here also glue these local tensors together and then create a quantum state. But the point is that now you have much more efficient representation of your quantum state, which works for representing basically many quantum states. Okay, but the question is it possible to represent any desired state in tensor network form? And the answer is no. So basically, as you see here, this D, this size, which is here, is amount of entanglement that you have in your system. So the tensor network representation are efficient if the entanglement in your system is relatively low. And then it means that if you look at many-body Hilbert space for the, let's say, a Hilbert space of a Hamiltonian, only a small pieces or a small subspace of this many-body Hilbert space is suitable for finding their state, for finding tensor network representation for these states. And these are basically the area law states that the entanglement is actually a scale in those states with the area of your system. Okay, now the question is how if I have a Hamiltonian, how I can find these states, this tensor network representation. Again, there are different approaches. So traditionally, one of the most famous approaches to approximate the tensor network representation of a wave function is the DMRG algorithm that basically is a very old and well-known approach in the community. Basically, what you can do is that you can variationally optimize the parameters of this tensor such that the energy of your Hamiltonian is minimized. This is the typical things that DMRG approaches are using. However, there are also other approaches based on time evolution. Imaginary, for example, imaginary time evolution, that you break the Hamiltonian by some Suzuki trotter decomposition and apply iteratively these trotter gates on your initial states, and then the ground state converges to the, the initial state converges to the ground state of the Hamiltonian. So basically, we will focus mostly on these time evolution approaches and discuss some of the challenges that we try to resolve. Okay, so now what I basically showed you was was the general ideas how these tensor network approaches work. But the point is that when you have a tensor network, the most important thing that you should do is to basically contract these tensors together to obtain your quantum many-body wave function or quantum state. By contraction means summing over all of these connections. So this operation is a very complex operation. So if you have a one-dimensional tensor network such as MPS, then it is easy. You start from here, do the contraction, reach the end, and your life is easy. However, PEPS in 2D and 3D, the contraction of PEPS is a basically very complicated an NP-hard problem. It is not something that you can do exactly. That's why people usually refer to approximation techniques. For example, there are some renormalization approaches based on so to say, corner transfer matrix renormalization group. That, for example, if you have your ket and bra and you want to calculate the norm of your wave function, you basically approximate the wave function for an infinite system with some, let's say, boundary tensors and do some renormalization approach. And you can actually, for every two-body operator, you can approximate the whole environment around it, then sandwich the operator with this environment and calculate the expectation values. It has basically large application in studying phase transition in quantum many-body system, and also calculating expectation values of operator and correlation. However, the challenge is that this approach, while it is powerful, it only works for a square geometry or a square lattice. Now the question is that if you want to apply tensor network to other lattices, or let's say in the ideal case, go and simulate Hamiltonians of, let's say, materials on real structure, then what would we should do? So, sorry. Okay, so in 2D, still there are some approaches to do this contraction. Usually, if you have a complicated lattice structure in 2 dimension, you can rather do some coarse graining, such as, for example, this is star lattice. If you basically group 3 sides together and represent the Hilbert space by 2 to the power 3, for example, for a spin 1/2, you can still map it to a square lattice and do the same approach for renormalization and then contraction of the tensors. Or you can actually, for example, if you have a triangular lattice, you can also break these sides or fine grain it and represent it with 2 tensors, and again you obtain the square lattice and then do this renormalization. But this is not the approach that you can do for any generic architecture. That's why we in efforts to solve this problem, we developed a graph version of tensor network, which is a graph projected entangled pair state, which is tensor network on a generic graph. This approach, basically our intention was to extend the application of tensor network to any desired lattice in any dimension. So you can consider basically, in this approach, basically we consider any lattice geometry as a generic graph, and then we apply our tensor network on every links of the graph, and then to handle all of the updates and contraction, we basically encode all of the information for this graph into some data structure. We call it a structure matrix that basically all of the edges of the graph and all of the nodes of the graph are basically, they have some numbers. These numbers basically explain which link is connected to which other link, and then you can easily, by looping over edges of the graph, you can update it and also contract this graph. So this is actually the approach that later I will show helps us to also simulate IBM quantum computers as well. It's not just only the application in basically quantum many-body physics and Hamiltonian simulation, but you can also use it for circuit simulation. Okay, so on top of that, so we also developed a more flexible version of this graph PEPs, which is, we call it flexible PEPs or lattice-free PEPs. So in this approach, we thought that basically in some of the quantum computing frameworks, basically the qubit topology is not necessarily connected on a lattice structure. That's why how we can represent a state in this kind of lattice-free state. What we do is that we start from some product state or some tensors here, which has no connection, and then we start to add entanglement between every 2 of them, which are connected rather by a basically 2-body gate or 2-body Hamiltonian, and then we let this connection and entanglement grows, and if the entanglement is negligible, we basically remove this connection, and then in the end, not only we obtain the solution to our Hamiltonian, which could be the ground state, we can also optimize this architecture of the or the structure of this graph itself. So this is also give us a lot of flexibility to simulate the Hamiltonians or quantum or classic cost functions in many different settings. Okay, so now let's see how we can use these approaches for some real application. So let's see how we can simulate quantum chemistry problems with tensor networks. I think in the previous two talks, it was already discussed that when you have for example, Hamiltonian of for example, a molecule obtained by some Hartree approximation, what you can do is that you can rather use classical approaches or quantum to do the simulation. If you go for the quantum case, the typical thing is that you get a Hartree Hamiltonian and then apply some, which is a fermionic Hamiltonian, apply some Jordan-Wigner transformation, obtain some qubit Hamiltonian out of it, and then basically by qubit Hamiltonian, we usually call it a spin Hamiltonian. It's in terms of spin operators, Pauli operators, and then you can use any of your tensor network algorithm, for example, to simulate the ground state of this spin Hamiltonian. However, there is a drawback. The thing is that when you have the Hamiltonian for this structure, if they are still small, that's okay. You can basically do Jordan-Wigner transformation and do the simulation. But if you go to larger structure and more complicated, it is difficult. So for example, here you would see that there are some energies for small molecules that we have good agreement with the DFT calculation. For some of them, we have even obtained lower energies. But if you go to very complicated structure, these approaches are not really optimal because this Jordan-Wigner transformation creates long-range Hamiltonians. The solution is to directly work with the fermionic Hamiltonian, such as, for example, the Fermi-Hubbard model, which is one of the candidate models for superconducting, and basically is one of the applicable fermionic models. But the point is that if you want to work with fermion for tensor network, you have to know that fermions are different from bosons. The wave function is antisymmetric with respect to commutation of particles. That's why you have to take care of these minus signs that comes from the basically exchange of particle into your tensor network theory. This we can also handle by these swap tensors that we introduce into the tensor network that takes care of basically fermionic exchange. And then here, for example, in one effort, we try to simulate the graphene, which is represented by a spinless fermion, and basically we showed that actually you can obtain the exact energy. This is an exactly solvable Hamiltonian, but with fermionic tensor network, we were also able to simulate the energy, which is -3 here, and it has very good agreement with the exact solution. Okay, so not only we can simulate a spin Hamiltonian and fermions, we can also simulate bosons. So for example, this is also one example of a simulation we did for the Bose-Hubbard model on the cubic lattice. That we also simulated basically different properties of these model and phase transition both at 0 and finite temperature. This is the physics that you will probably find in optical lattices. The temperature is low, but it is not absolute 0. That's why also we can simulate finite temperature with tensor network that presents here basically the transition between mott insulator, superfluid, as well as when the temperature increases and then the system evaporates to normal gas. All right, so these are some applications, but in the last part, I will also show you some example of tensor network for circuit simulation. So I showed you this picture when I was talking about how to approximate this tensor network representation of Hamiltonian, but this is very similar to what you would see in a quantum circuit. So like in the imaginary time evolution, we have this evolution gate applying on some random tensor to obtain the grounded state of a Hamiltonian. However, this is very similar to what you would do. You apply some basically gates that altogether form a circuit, and you can basically apply them on some product state originally. So this product state can also be represented in terms of tensor network with 0 entanglement, and then you can apply these gates and basically generate entangled state easily by tensor network approaches. So like at the last part, so this is actually one of the things that we use to simulate the IBM experiment that basically they showed that they observed evidences of quantum supremacy on their Eagle processor, which was 127 qubit. They simulated basically the dynamics of Ising transverse field model on this lattice with this connectivity. This is called the heavy hexagon. This is the lattice that represents the Eagle processor. So we used our GPEPs or graph projected entangled pair state and exactly simulated these unitaries that is equivalent to this Hamiltonian, and actually showed that we can efficiently, in a very efficient and fast way, we can simulate not only the exact solution, but also the results that is obtained from quantum computer. Also, previously there has been some tensor networks simulation that basically the IBM claimed that they are failing when you compare them with quantum computer, but we actually shows that it is very important to choose the correct tensor network ansatz when you are simulating the relevant quantum circuit. And these are the results that perfectly matches for magnetization for different, let's say, rather average or for a cluster of sites on the lattice. And in the end, also, you can study time dynamics with large trotter steps, and you see that still you can go very long times, study very long time dynamics if you basically allow the entanglements to grow sufficiently. And these ansatz are very efficient, not only for circuit simulation, but also for basically time dynamics calculation. And with this, I would like to summarize. So tensor networks not only are used for just generically for representation of quantum state, but they have many applications for, let's say, optimization for rather quantum Hamiltonian or classical cost function. For example, like many good applications that you can find with in finance, logistic, energy, which is relevant to solving some Kubo problem or Hubo problem. You can basically solve them with tensor network. Also, like quantum annealing processes, you can simulate them with tensor network, and also for circuit simulation. This is actually one of the things that we are currently working to create an enhanced one. You can execute any desired circuit that you like in an efficient way with tensor network. It just it can be a circuit that is composed of quantum gates or a Hamiltonian or time evolution gates, and then obtain the entangled state or study their time dynamics. In the end, and also this is something relatively new, that we started to also use tensor network for generative AI and deep learning model that not only allows us to compress and find more efficient large language models and deep learning model, but also optimize them in a different way, such that we preserve relative amount of accuracy for this model while consuming like insanely smaller amount of energy that basically thankfully is obtained by using a compressed version of tensor network for representation of weights of a large language model. And with this, I would like to thank you.
Okay, thank you, Saeed. We have only time for one quick question, I think, and have to do the others in the lunch break.
Hi, thanks for the nice talk. I had just a naive question, maybe. How do you decide the optimization strategy in this graph PEPs? Like, what is the order of the optimization in a DMRG?
Well, in principle, depending on the optimization problem, you can use different approaches. So this is originally an unknown question, which ansatz or which theory you should use. It depends on the problem. But for example, for classical optimization problems, such as this Kubo that has many applications in finance and let's say engineering and etc., we found that MPS and rather DMRG or let's say this time evolution usually works better. You don't really need to complicate the problem to go to a complicated graph. But of course, you can use that and maybe obtain the same results, but the computational cost of MPS is usually cheaper. That's why it is advised that you go with that. However, if you have a problem which is on a 2D or 3D or even a generic graph, then of course this GPIPS is the optimal choice for you to start and see what you would get out of the optimization problem.
Yes, but within this graph MPS, PEPs, sorry, how do you decide the sequence of sizes to optimize? Like, do you optimize in which order?
This is again also something that you can play with, and then depending on the final results that you find, basically decide how to apply. But the thing is that when you want to apply, for example, use these time evolution approaches, you basically terratorize your Hamiltonian or your cost function, and then when you try terratorize it, and then the order at which you apply this operator on different sides, it doesn't matter, especially if they are far apart. So basically, you can experiment with different approaches and see which one gives you the quicker and faster results. Okay.
Yeah, also sorry for cutting the discussion short and putting it to the break. Let's thank Saeed once more.
Okay.